So we're going to be talking about relations and functions, and we're going to start with relations. Now remember that if A and B are two sets, the product set, notated as A times B, was just defined to be the set of all possible ordered pairs. And specifically, there's an order in an ordered pair. Okay, the notation is A times B is all possible ordered pairs so that the left element of the ordered pair was from the left set A, and the right element of the ordered pair was from the right set B. And formally, a relation is just any subset of this product set. So some possible collection of ordered pairs. Could be the empty set, could be the entire set, could be something in between. Intuitively, however, we're going to be understanding relations as implying some sort of relationship between the elements. So specifically, if we have a particular ordered pair in the set R, we can use set notation, and we can say that ordered pair is in the relation. And we're going to use this notation if we want to emphasize set theoretic properties of relations. But we can also write this. When we have a relation that implies some sort of meaning, and we want to understand it on that level, we can say A, R, B. Notice there is an order to this, okay? Because an ordered pair has a left and a right, we preserve that order here. Neither notation is inherently better than the other, they're just used in different situations. So the former notation is our general set theory notation, but the second one suggests more of a relationship between the two items. We can say A is related to B when we have this written, and we could also say R relates the set A to the set B, or A is related to B in terms of the sets, not just the elements, okay, by the relation. When we have a relation on the sets A and B, we can say R relates them, or A is related to B by R, and it's just a possible collection of ordered pairs. Now, there are going to be some sets that we commonly use when talking about relations. We haven't formally defined them, but we're just going to start using them. Okay, the natural numbers, also known as the counting numbers, 0, 1, 2, 3, and so forth. They're written with this capital N, where this is a double bar diagonally. Conventions do actually vary from place to place. Sometimes 0 is or is not included in the natural numbers. I am going to be including 0 as a natural number. The natural numbers have a lot of interesting properties. To set them apart in terms of Zermelo-Fraenkel set theory, we're going to put that off for a little bit. We just basically understand what these numbers are. We're not building up a formal definition here. Okay, next we could talk about the integers. Compared to the natural numbers, this just throws in negative numbers as well. Okay, and that's how we understand them intuitively, not just the counting numbers, but also their negatives. Now we have rational numbers here, and let's look at how we've written this. The set of rational numbers is the set of all P over Q, where P and Q are both integers and Q is not 0. Okay, now these are ratios of integers, provided we don't have a 0 denominator. Notationally, note also integers are Z with a double bar, and rational numbers are Q. Sort of handwritten, so this is the typeface version. Handwritten, we tend to write it like this. Okay, we put that double bar just on the left. Okay, then we have the real numbers R, and again, this is the typeface version. Handwritten, it tends to just have a double bar on the left. Now, a formal definition of what the real numbers are is way more complicated than we want to get into. But most people have this intuition based on the notion of a number line, and honestly, that's going to be good enough for us. Okay, as I've said, we're not formally building up all these number systems. The natural numbers, the integers, the rational numbers, the real numbers, we all have pretty good intuitive understanding of what they are, and that's going to be fine for now. Okay, we're also going to assume that we can do basic arithmetic. If I put something up about adding numbers together or multiplying them or exponentiation, it's going to be assumed that we all know how to do that. So let's look at some examples of relations. So suppose A and B are both the integers. I'm going to define a relation R to be an ordered pair of one integer comma another integer belongs to this relation exactly when their sum is 0. So 3 is related to negative 3 because they sum to 0. But 2 is not related to 5 because 2 plus 5 is not 0. So all we have is we have a collection of ordered pairs of something that adds to 0 with the other one. Another example, natural numbers and rationals. Notice these don't have to be the same set. So what I have is a natural number, comma, a rational number belongs to my relation exactly when their product belongs to the set of integers. So 4 is a natural number and it is related to 1/2, a rational number, because 4 times 1/2 is an integer. 4 times 1/2 is an integer. 9 is not related to 1/2. 9 is a natural number, 1/2 is a rational number, but their product is not an integer. 9 times 1/2 is 9/2, which is in between 4 and 5. Okay, we could also, for example, have A being the reals, B being the integers, and say a real number is related to an integer when it's bigger than it. So pi is related to 2. Okay, pi is a real number, 2 is an integer, and indeed pi is bigger than 2. That's a true statement, so pi is related to 2. But 2 is not related to pi, and it's not just because 2 isn't bigger than pi. Specifically, there's a right and a left notation here. The first number has to be real, the second number has to be an integer. I can't say 2 is related to pi because pi isn't even an integer, so it's not even a candidate that could have been in the product set a times b. It was never going to be in any relation between them. Okay. There's no requirement, however, for relations to be defined with arithmetic. Any subset of the product set can be a relation, so it doesn't have to be something you define using arithmetic, it could be something totally different. But arithmetic happens to make very convenient examples because we can write them down easily and discuss them using skills we've already developed in other courses. So those were relations. What are functions? Okay, relations were very, very general. Any subset of the product set can be considered as some sort of relation from A to B. But there are special types of relations that we're going to develop further. For example, a function is a relation, okay? So it has to be a subset of the product set, but it's going to have some additional properties. Given any element of the first set, notice that this is specifically from the first set of the product set, given any element of the first set, there does exist something in the second, so that the ordered pair belongs to that relation. Given any element of the first set, now I have a conditional statement, if there exist two elements of the second, so that a comma b1 is in the function and a comma b2 is in the function, this will always imply that b1 and b2 were the same thing. Okay, so what do these say? The first says every element of the first set is related to something. Every element of the first set, there is a thing that it's related to. The ordered pair belongs to that relation. The second says, fine, the first says everything's related to something. This one says if something in the first set is related to two things, then those two things were the same thing to begin with. In other words, you are not related to two different things. So everything in the first set is related to something, but not to two different things. So in this case, we can write the following. F is a function from A to B. This is how we read out this notation, sometimes also said as F maps A to B. And this notation emphasizes these special properties. If A comma B is in this product set, we write F of A equals B. This is functional notation, and it says if you take this element from the first set and, quote, plug it in, end quote, to this function, what you get out is the element B. The set A is called the domain of the function. These are the things that get plugged in to the function, the things that can be the left argument in the ordered pairs, and by this first condition, that's everything in A. Everything in A appears as the left term in an ordered pair of this function. So the set of things that we can put into the function, aka the set of things that appear on the left side of these ordered pairs, is actually all of A by this condition up here. That's what's called the domain of the function. The set B is called the codomain, and a lot of you were probably thinking that I was going to use a different word here. So the codomain is just the set of possible things to get out. This set is called the range. The set which are elements of the codomain such that there exists something in the domain that gets mapped to it. Okay, so this set here is all the things in B that actually do get out from plugging something into the function. That's called the range. In these conditions, there's no requirement that every element of B actually be given by some sort of f of A. The things that are given by some sort of f of A, that's what's called the range. Okay. So the range and the codomain do not need to be the same set. The codomain is just what set I put here or what set I'm mapping into. The range is what I actually managed to get out. So let's look at some examples of functions. First up, I have a function that maps natural numbers to integers given by a formula. If I plug in a natural number x, I get out 2x minus 4. So is this a function? Can I plug every natural number into this? And if I plug one number into it, is it possible to get out 2? So suppose I plug the number x in, and I get out the number y1, but I also get out the number y2. So this here says f of x equals y1, f of x equals y1. This pair here says f of x equals y2, f of x equals y2. Okay, the equality sign is transitive, so we can immediately claim if they're both equal to 2x minus 4, then they're equal to each other. And that's that second condition of being a function. Something from the domain was related to two different items from the codomain, and we were able to conclude that they were the same item to begin with. So this is indeed a function. Okay, we could also verify that every natural number can be plugged into this, but yes, any natural number we can multiply it by 2 and then subtract 4. What's the range of this function? Well, since the natural numbers are 0, 1, 2, and so forth, by plugging those in, we see we get out -4, -2, 0, 2, 4, 6, 8, 10, and so forth from there. That's not every integer. The codomain was integers. The range is this specific subset of the integers. Let's look at another example. I have a function whose domain is the real numbers, whose codomain is natural numbers, given by, if I plug in a real number, I find the largest integer which is not larger than the absolute value of x. So for example, if I plug in 11.4, the absolute value of 11.4 is just 11.4. What's the biggest integer that isn't surpassing that? The biggest integer that doesn't surpass 11.4 is 11. However, f of -11.4 is also 11. The absolute value of a -11.4 is 11.4, and again, the biggest integer which does not surpass that is still 11. This does define a function. I can plug any real number into it, and every time I plug a number into it, I'm going to get out exactly one thing. I cannot get out 2. The range is also all of n. Every natural number can be computed as the largest integer not bigger than the absolute value of something. Okay, but there are examples we can do that aren't based on algebraic expressions or computation. So suppose I have a function that maps integers to the set of letters A through Z, okay, where f of an integer is going to be given by the last letter of that number when written in English. So what's f of 10? Well, since the word 10 ends with n, f of 10 equals the letter n. f of 38 equals the letter t because the last letter of the word 38 is t. It's certainly a function. Every number can be written in English, and then every number does have a single letter, which is the last letter. So I can compute f of any number, and I'm only going to get out one letter. So I can plug anything in, and I only ever get one thing out. But it's not some sort of computational method, okay? But it's still a function. It's a way of assigning to everything in the domain exactly one element of the codomain. In summary, any subset of a product set can be considered to be a relation, where the ordered pair A comma B being in the product set means A is being related to B. That's a very general construction, and usually we're actually interested in relations that have some specific properties. Some of the properties we're going to talk about later, but in this video we introduced one more, the notion of a function, which has additional properties. Not only is it a subset of the product set, but also every element of A is related to something, but nothing in A is related to 2 or more different elements of B. So that's what a function is. A function with domain A and codomain B says every element of the domain is mapped to something, but not to more than one thing. That's a function. Okay, so for functions, we are going to use familiar notation like f of x equals y, but remember, if we write this, f maps a to b, or f is a function with domain a and codomain b, the range is not necessarily b. The range is specifically the subset of b, which is actually achieved by plugging things from a in. So the stuff that you actually get out is called the range. The codomain is just whatever set you happened to put there.